you know that before the invention of mechanical gears and batteries, the ancient world used leaking bottles to tell time? These were called clepsydras, or water clocks. The Greek Egyptians realized that as the water level dropped, the pressure decreased and the water flowed out slower, which made their clocks inaccurate. To fix this, they had to master the exact relationship between the water head and flow rate. These are the same principles of fluid mechanics that we will demonstrating through our experiment in this video. To see these theories in actions, let's start our experiment and walk through the procedure we follow. These are the apparatus that we need for the experiment. 2 types of straw with different diameters, 2 plastic bottles, a screwdriver, measurement tape, scissors, vernier caliper, tire pump, and marker. Now, let's move on to our experiment. First, we begin by preparing 2 bottles with 3 orifices drilled at different vertical heights, 3 cm, 8 cm, and 18 cm from the base. This level allows us to observe how hydrostatic pressure changes relative to the depth of the water. For our first trial, we use an orifice diameter of 5.4 mm. We fill the bottle, and as the water reaches each mark line, we measure the horizontal distance of the water streams. As you can see in this footage, the water from the lowest hole, which has the highest water level above it, travels the furthest distance. This is because the hydrostatic pressure is greatest at the bottom, forcing the water out at a high speed. We record these distances carefully to use in our next calculation. Now, to see how we can manually increase this flow, we introduce a bicycle pump to the system. This mimics real-world applications like irrigation pumps or engine compressors, where we are not just relying on gravity. Can you notice how the velocity of the fluid increases immediately as we create external pressure? This demonstrates that we can bypass the limits of gravity and water level height by adding mechanical energy to the system. The streams reaches much further than it did in our previous trials because we have artificially increased the internal pressure of the bottle. Finally, we repeat the entire experiment using a smaller orifice diameter of 2.8 mm. This comparison helps us to conclude how the size of the opening, combined with the water level height, ultimately dictates the final discharge rate.
Purchase your track today.
Now that we have completed our trials, let's take a look at the data. By analyzing the measurements we recorded, we can clearly see how the water level and orifice size impacted our final discharge rate. To summarize, our result shows why water height provides initial pressure, external forces and orifice size are what ultimately control the speed and volume of the flow. These principles are vital for drainage systems, irrigations, and oil pumping. I hope you enjoyed this look into the physics of flows as much as we enjoy conducting the experiment. Thank you for your time and for joining us on this journey through fluid dynamics. Thanks for watching. Bye-bye.